Okay, welcome again to the European Non-Associative Algebra Seminar. It's a pleasure to introduce the speaker of today, Professor Ignacio Bajo from the University of Vigo. We talk about quadratic Lie algebras admitting two plectic structures. Please.
Okay, first of all, I want to thank the organizers for this kind invitation to give a talk at the seminar. And okay, the title of my talk is actually Quadratic Lie algebras admitting two plectic structures. It is a joint work with Saïd Benayadi, who is at the University of Lorraine in France. And well, I'm going to give an idea of what a two-plectic structure is on a Lie algebra. Our problem comes, in principle, let's start with some preliminaries if you want to. And the main problem is a geometrical problem that comes from physics. And actually, to describe some field theories in physics, one has to reformulate in some sense that some infinite dimensional variational approaches are considered in multi-phase spaces. So multi-symplectic geometry deals with that situation. It is a situation that is, well, the first works concerning this multi-symplectic geometry are from the 60s and 70s. But the main problem that that physicians have is that there are not many examples of manifolds with multi-symplectic structures. So we wanted to give a large number of examples, and obviously Lie groups in geometry are a nice way to obtain many examples. So let's start with some geometrical definition, which I know that most people here are algebras, but well, these are very simple ideas. So a k-plectic structure is just a k+1 form on a manifold, such that it is closed, and it is non-degenerate in that sense, in the sense that if we take one x in the tangent bundle, and we introduce it as the first variable of our form, then the k form that results is different from 0. There are two very well-known cases. The first case is a one-plectic manifold, which is the classical notion of symplectic manifold. And notice that when you have an n-dimensional variety, then an n-1 plectic structure is nothing but a volume form. So I also want to mention that there is a different concept that was introduced by one, which is, it sounds very similar, but it is a very different thing. It is the concept of a k-symplectic manifold. In a k-symplectic manifold, one, he defined them as a manifold with k-closed two forms, verifying certain conditions, right? The kernels are have no intersection, and they have a common subspace which is isotropic. So here both things are different. A k-symplectic structure is not a k-plectic structure, and the contrary also holds, but except in the case that k equals 1, in which we have, in both cases, we have a natural symplectic manifold. So okay, since we are going to work on Lie groups, then we can pass everything to the Lie algebra. So we can always work at the Lie algebra level. So we are going to do everything algebraic. So, okay, what is then, we take a Lie algebra, and what is a two-plectic structure on a Lie algebra? This is nothing but a three form, which is non-degenerate and closed. This means, what is a three form, a closed three form? Well, this is the same thing that a three co-cycle for the scalar cohomology, right, of the Lie algebra, and which is non-degenerate in the sense that if we take one x different from 0 in G, and we put it in the first variable, then the 2 form that we get is different from 0. And well, the condition to be closed, this is to say to be a 3 cocycle, is this one that appears here. So that is just the definition right there. Okay, obviously we can have that there are 2 plectic structure is actually a coboundary, and in that case, in geometry, one usually says that it is exact. So we will use also that terminology. So an exact 2 plectic structure will be a 2 plectic structure in which the form is actually the differential of another 2 form. Okay. All right. Now, oops. Oh, this doesn't. Okay. All right. First thing is, can we find simple examples in the algebras of these constructions? And well, there's a very, very simple construction, which is just take a symplectic Lie algebra. This means just a Lie algebra with a non-degenerate closed 2 form, right? And a derivation, which is a skew symmetric with respect to the form. And then you just make the semi-direct product of G by the derivation, and then define this 3 form here in that space in the semi-direct product, right? And that results to be a 2 plectic structure. Further, if the symplectic structure that you get on G is actually exact, then this 3 form is actually exact. So we can find in Lie groups or in Lie algebras, we can have both situations. We can have obviously 2 plectic structures, and we can also have 2 plectic structures which are exact. But the problem is that these cases are somehow quite trivial. I mean, you just have something with a very strong condition, which is to be symplectic, and you just do a one-dimensional semi-direct product. So this does not give many examples. All right, I don't know what. No, sorry. Okay. Okay, this is the one of the examples, which is low dimensional. You just have a 3-dimensional case. Notice that here you have what we have is actually a volume form, right? And it is the case of the Lie algebra of fine motions of R multiplied by R, just the direct product. And then one say that there you can find actually an exact 2 plectic form. Okay. Some known facts. The first thing is that if you have a direct sum of 2 Lie algebras and both are 2 plectic, then you can construct obviously a 2 plectic structure in the product Lie algebra just by doing the product of both structures. Second thing is that we can have 2 plectic forms in any dimension except the 2 obvious dimension 1 and 2 and dimension 4, because in dimension 4 it is impossible to have it can be seen that you cannot have a non-degenerate 3 form. And one thing that is very well known, and actually was mainly the only example known of these structures on Lie algebras, was the case that every semi-simple Lie algebra admits a 2 plectic form. And the 2 plectic form is given by the Killing form on the Lie algebra applied to a bracket xy and z, right? So this, when K is the Killing form of the Lie algebra and the Lie algebra is semi-simple, then you get that 3 form, it is actually a 2 plectic form on the Lie algebra. So this gave us an idea of how could we work with other kind of Lie algebras. And because Said Ben Ayadi and I had worked a lot on the so-called quadratic Lie algebras. Okay, so what's the quadratic Lie algebra? Quadratic Lie algebra is a Lie algebra which is endowed with a bilinear non-degenerate symmetric form, such that multiplications in the Lie algebra, this means at x, are skew-symmetric maps, right? So these conditions also come from geometry. Actually, if one thinks of this geometrically, this means that the Lie group is endowed with a pseudo-Riemannian both left and right invariant metric, a bi-invariant metric. Okay. Some authors, they call the algebras quadratic. We will call them like that because we are following the ideas of Alberto Medina. But there are some other names for these metrics, for this Lie algebra. Sorry, some authors call them metric Lie algebras or metrized Lie algebras. Well, actually, the first example of a quadratic Lie algebra is semi-simple Lie algebras with their Killing form, which are obviously quadratic. So, since the Killing form gave a plectic structure on semi-simple Lie algebras, we thought that it was quite reasonable that on every quadratic Lie algebra we could find somehow a plectic form which can be constructed with the quadratic form. But this is not exactly the case, although in many cases one can. Sorry. So let me just recall a couple of results concerning quadratic Lie algebras. Quadratic Lie algebras have been are very well studied, and one of the interesting results is Medina-Rivoire's result, which gives a method to construct quadratic Lie algebras. And that method is called quadratic double extension, because actually one starts with a quadratic Lie algebra D0, and then one does two extensions. First, one does this, which is going to be a central extension, and then one takes a semi-direct product by a certain derivation. And well, this is exactly the way that is worked here, that works here. But the derivation and the central extension have certain relationship. And actually, if you see here, this is the part of the centralization. You see that the centralization is actually constructed by with the same derivation that we take for the semi-direct product. Okay, this method known as quadratic double extension by a line because here we take a one-dimensional subspace, because one can make this similar construction also for other Lie algebras. But in our case, this will be sufficient. And it is interesting because there's a result of Medina-Rivoire that says that every solvable quadratic Lie algebra can be constructed by a series of double extensions by lines. So actually, one can start from an abelian Lie algebra, and one makes double extensions, and one gets the initial quadratic Lie algebra. Okay, besides this, there's another construction which we will use, and it is Bodeman's T-star extension. T-star extension is another way to construct the algebras, and which was proposed by Martin Bodeman, and based a little bit on the construction which was very well known in geometry, which was the cotangent algebra of a Lie algebra. Actually, one takes a Lie algebra G, and in principle a two cocycle for the complex defined by the quaternion representation, and then on this space one can define under certain conditions, and the condition is this condition of cyclicity. Then on this space, on the vector space G plus G star, one can construct a natural pairing, which gives a quadratic structure. Here, if this theta here modifies a little bit the bracket, And the well-known case in geometry, which is the case of cotangent algebra, is the case in which theta is actually 0, right? Okay, Bodeman showed that actually all these Lie algebras under these conditions are also quadratic Lie algebras. And further, he saw that in the complex case, every solvable quadratic Lie algebra is either a T-star extension or an ideal of codimension one in a T-star extension. So in the complex case, actually in the algebraically closed case, they give more or less all the solvable cases. Okay, this will be useful afterwards also, so just to recall, although mainly we will work with the case theta equals zero, but sometimes we will make some constructions, especially for the case of exact two plectic forms, which will use a non-zero theta. Okay, next. Oh, sorry. Okay, a few things is that well, these things that I have already told you, the case theta equals 0 defines the cotangent Lie algebra. The main problem with T-star extensions is that non-isomorphic Lie algebras may have isomorphic T-star extensions, so it is not so good to classify and to make classifications, but it works very well to make new constructions of quadratic Lie algebras. Okay. Right. Sorry. Okay, so let's start with the first example of quadratic two-plectic Lie algebras. And our first cases are on perfect quadratic Lie algebras. Lie algebra is said to be perfect when it coincides with its derived ideal. And these Lie algebras, when they are quadratic, are equivalent to be centerless Lie algebras. So a quadratic Lie algebra is actually just a perfect Lie algebra is just a quadratic Lie algebra which has 0 centers. It is very easy to see that there are non-semisimple quadratic perfect Lie algebras. For instance, if you take a semisimple Lie algebra and then you take its cotangent algebra, so you make the T-star extension by 0, then you get a new Lie algebra which is actually perfect. It is quadratic, and it is not semisimple because it has the part of the dual is in the radical of the Lie algebra. Well, it's actually the radical of the Lie algebra. Okay, next. All right, what happens in these Lie algebras? In these Lie algebras, we can do the same construction as for the semisimple cases. So if we construct the two-plectic form given by B of xy, bracket of xy, z, then we get two-plectic form. The main problem is that when we work with non-perfect quadratic Lie algebras, we cannot use this. And we cannot use this because in a non-perfect case, we always have a non-trivial center. And when one has a non-trivial center, then one obviously has that this is 0. So the condition of non-degeneracy is not okay. So it doesn't work. So in the non-perfect cases, which were the cases that were more interesting for us because we wanted to have a lot of examples in solvable cases, we cannot do this construction. It is true that one can see one thing, that one can make a quotient by its center, and then one gets something, but then the Lie algebra, then it is not quadratic in the general term. So let's see if we can have another constructions. And the fact is that we found a construction which is very nice, and is this construction of a family of nilpotent Lie algebras, which can be constructed starting from any two-plectic quadratic Lie algebra. So suppose that we take any two-plectic quadratic Lie algebra, which can be semi-simple if you want to, And then we construct this nilpotent Lie algebra, which is given by S copies of the same Lie algebra. GT1, GTS actually are just copies of the Lie algebra G. But when we define the bracket in the following way, we make the bracket xti ytj is xy ti plus j. So and from some number bigger than s, then we go to 0. That makes the Lie algebra an nilpotent Lie algebra, actually of s steps maximum, and it is quite simple to see that we had already seen this in a previous paper, that these Lie algebras are always quadratic. One can be taken this quadratic form, and we saw that they are also two-plectic, and that this W tilde give us a two-plectic form on this nilpotent Lie algebra. And that result, which is just, obviously, it's just an example, but it is a very interesting example, because this shows that this corollary, that if we take that our Lie algebra is perfect, then the construction gives exactly a nilpotent Lie algebra, which is S-step nilpotent, strictly S-step nilpotent. I mean that it is not S-1 step nilpotent. And as a consequence, we have that we can always construct for every step of nilpotency, we can always find a nilpotent quadratic Lie algebra which admits into plectic structure, which was not so trivial, it was not so obvious. Okay, so this construction led us to another type of construction, which was done with tensor product. This is another very well-known way to construct quadratic Lie algebra, starting from a quadratic Lie algebra. And it is just tensorizing, making the tensor product with an associative commutative algebra, such that has as a non-degenerate symmetric bilinear form, verifying this associativity condition. Right? Well, in the case that in our case, if we have that our Lie algebra, our associative algebra has a unity, then we have that the tensor product is actually a two-plectic quadratic Lie algebra, defining just the two-plectic form in this way. And there are two very interesting cases. The first case is that the complexification of every real Lie algebra, which is two-plectic quadratic, is also two-plectic quadratic. The complexification that's seen as a real Lie algebra, and the tangent algebra, which is something similar to the cotangent algebra. In the cotangent algebra, we had the sum of G plus G star, its dual, and it was a semi-direct product done by the quadjoint representation. But here we have the same thing for the tangent algebra, but we take the adjoint representation. And it can be seen that it is also of this form, right? It's just G tensorized by this associative algebra A given by these brackets. Okay, so for every two-plectic quadratic Lie algebra, we have that then both its complexification and its tangent algebra are again two-plectic quadratic. So now we start to enlarge our number of examples. So okay, but the main fact here for us was to see if we could make, let's say, if we could profit of the double extension method to construct a new Lie algebra starting from a Lie algebra which is two-plectic in a dimension which is larger than the given one. And so we started to see what happened in these cases. So our first result, which was practically our main result, was to give conditions under which we could extend a closed tree form on the middle Lie algebra to a double extension, and to see under which conditions we could have that the new extended form will be at least closed. Maybe degenerate, but at least closed. Okay, the conditions were these conditions, which are quite technical. I'm not going to stop there. But notice that here we have not imposed the condition of being quadratic. We have just the Lie algebra with a closed tree form. And this was because we were thinking that maybe also in the symplectic case, where there is something similar to a quadratic double extension, but in that case it is called symplectic double extension, maybe we could also profit of this result. But in the case of a quadratic Lie algebra with a closed tree form, then the conditions tend to be this way, which are a little bit more simple. So we have to find some skew-symmetric maps F and P verifying these conditions here, and then A0. So the closed tree form lies on two skew-symmetric maps and an element of G. Okay, so with this, can we have a good method to describe all the cases? And the fact is that not, but this conditions doesn't seem to give all the cases, but they are a very nice way to construct some interesting examples. So first of all, we start thinking on what happens for trivial extensions. And I know that the problem seems too stupid, too simple, but the fact is that it is very simple to see that if you have a two-plectic Lie algebra, which is quadratic, and you just take the trivial extension, so you just take the direct product with R, and sometimes that new algebra doesn't have a two-plectic form. And the more easy example is you take a three-dimensional Lie algebra, which are always two-plectic. You take a direct sum with R, and you get a four-dimensional Lie algebra with never is two-plectic. So that was the one of the easiest counter examples to our conditions. But we arrived to see that if you have a quadratic two-plectic Lie algebra and you make a direct product with something which is at least a plane, let's say that you have the direct sum with RK with K bigger than 1, sorry, then you always can construct a two-plectic structure. In the case in which you have G plus R, here the main problem is that you cannot always extend the two-plectic structure that you have in the small Lie algebra in G to the large Lie algebra. And one of the cases is this. Here, if you take a perfect quadratic Lie algebra that has no outer derivations, which are skew-symmetric with respect to the quadratic metric, then the two-plectic form defined naturally on the perfect Lie algebra cannot be extended to a two-plectic form on the trivial extension by a line. So that shows that the problem of trivial extensions, although it is resolved, or apparently it's very, very simple, but it is not so simple. And actually, I have to say that we do not have a complete answer to the question. We do not know if we can always have a two-plectic form on this Lie algebra, except for the cases that are mentioned here. But there are some cases in which we can say something. And the first case was in the case of for instance, two-step nilpotent quadratic Lie algebras, in which one says that if one has that dimension of the Lie algebra is bigger than 10, then G is two-plectic. If G is two-plectic, then the direct sum of G plus R is also two-plectic. And this condition, well, it is under a condition that the center must be the derived ideal, but in two-step nilpotent quadratic Lie algebras, that is not very restrictive, because otherwise you just split in the parts in which this is verified and an RK, and then you apply the result that we have seen before. So actually, one also can see that up to dimension 6, I think, if I am not wrong, every two-step nilpotent quadratic Lie algebra is also two-plectic. So we only don't know what happens in the 8-dimensional and 10-dimensional cases. There are some classifications of quadratic nilpotent Lie algebras in those dimensions, but we did not take the time to verify and they admit two-plectic. But I guess that actually every two-step nilpotent quadratic Lie algebra has a two-plectic form. Okay, but obviously these cases are again quite restrictive. So we started with another case which was gave a large number of Lie algebras, and were the cases of quadratic symplectic Lie algebras. This is actually from where this work came from. And it was from a work by me, Benayadi, and Medina, in which we had studied symplectic structures on quadratic Lie algebra. So we had seen the, let's say, one plectic case, right? And well, it is very easy to see that in that case, the symplectic form can be given by the quadratic case, the quadratic structure, and an skew-symmetric invertible derivation. And according to a very well-known theorem of Jacobson, since the Lie algebra admits an invertible derivation, then it must be nilpotent. So this kind of quadratic symplectic Lie algebras only appear in the nilpotent case. One also can see that not every nilpotent case has invertible derivations, so most people know this. So not every nilpotent Lie algebra is quadratic symplectic, obviously. Okay. Now, the main theorem, which was not so simple, but it was very heavily based on the theorem that we had seen before concerning double extensions, is that if your Lie algebra has dimension greater than 4, recall that with dimension 4 we have no two-plectic form on Lie algebras. Well, from dimension 4 on, we have that every quadratic symplectic Lie algebra admits a two-plectic form. And further, we can see that if one has a Lie algebra which has an invertible derivation, now take this proposition, we take H is a Lie algebra which needs not to be quadratic. We just have an invertible derivation, the Lie algebra, and then we can endow the cotangent algebra with a two-plectic form, because actually we can endow the cotangent algebra with a quadratic symplectic structure, and so according to the theorem, then it has a two-plectic form. And this is the case of every two-step nilpotent Lie algebra. If we take H, the two-step nilpotent Lie algebra, then its cotangent algebra is also a two-plectic Lie algebra. All right. Well, and remember that at least in the complex case, one has, according to Bodemann, that every nilpotent Lie algebra, every nilpotent complex Lie algebra, is a T-star extension of a nilpotent Lie algebra, or an ideal of codimension 1. So if the two-step nilpotent Lie algebra we take is admits an invertible derivation, then we can have a two-plectic struct. All right. But now we also want to construct non-nilpotent cases. So we started to think what happens if we now take a quadratic double extension of a quadratic symplectic Lie algebra. And in that case, we saw that if the center is not totally isotropic, then the double extension done by the derivation D. D is the derivation which links the quadratic structure and the symplectic structure. Then we get a solvable Lie algebra because D, as far as we know, it is invertible. So here we get a Lie algebra which is solvable and non-nilpotent. And then we get that these Lie algebras admit a true plectic structure. So all these cases give solvable non-nilpotent Lie algebras, and there are many cases that can be constructed in that way. And one of the cases that is very, very important, or at least very interesting for its importance in physics, is the case of the well-known oscillator algebras. The oscillator Lie algebras are the only Lie algebras which admit a quadratic form which is Lorentzian. Lorentzian in the sense that it has signature 1 n minus 1. So they are of index 1. Well, they are constructed that way. They can be constructed actually as the double extension by an invertible derivation of Rn, actually of R to n. And well, that is the definition. And they lay exactly on the case that we have seen in this proposition. So every oscillator Lie algebra, which have some importance in physics, every oscillator Lie algebra of dimension greater than 4 admits a true plectic structure. Excuse me. Okay. Okay. Just in order to finish our results, we wanted to see what could we say from for the cases of exact plectic structures. In many of the cases, I have seen some cases before in which we could find exact examples. But we did not know if these examples were very wide or not. So let's say a couple of things. First thing, an equivalent condition, which is very simple, is that the quadratic Lie algebra admits an exact true plectic form if and only if this condition is verified. There's an element in the Lie algebra of skew-symmetric endomorphisms of GB such that verifies that condition with respect to the bracket. Okay, so it's very simple that not every true plectic Lie algebra admits exact true plectic forms. In small dimensions, for instance, the simple Lie algebra of trace zero matrices does not admit an exact true plectic form. And one can also see that there are nilpotent cases that doesn't have exact true plectic forms, as for instance, the cotangent algebra of the Heisenberg algebra. Notice that this is a 6-dimensional Lie algebra, which is obviously quadratic. Well, actually, it is quadratic symplectic, and so it has true plectic forms, but it doesn't have any exact one. So what can we say in these cases? Well, here we found that T-star extensions were really useful to construct exact examples. And the first example was this proposition, which tells us that the T extension by the cyclic cocycle theta, in which the dimension of the small dimensional Lie algebra G is even. So our capital G is actually 4n dimensional, right? And one has that theta is not degenerate. Then the quadratic Lie algebra always admits an exact true plectic form. For instance, in the case that we have a two-step nilpotent quadratic Lie algebra with the dimension of the derived ideal even, then it always admits an exact true plectic form, which is quite an interesting result. because I notice that, for instance, in the cases, this is quite curious, but because for symplectic Lie algebras, you cannot have exact examples in something which has a non-zero center. But here you can. So you can have actually nilpotent cases in which you have that exact two-plectic forms exist. Okay. We can see that there are also many examples in perfect cases. So we saw that in the nilpotent cases, at least in many two-step nilpotent cases, we found these structures. But there are some cases in which are perfect, and we can also find this. So just to give the definition, to recall the definition of the centralizer of subspace in a Lie algebra, is just the elements of the Lie algebra that has bracket 0 with all the elements of the vector space V, right? And then we have this result in which we suppose that we have a perfect quadratic Lie algebra. Recall that perfect means that for a quadratic Lie algebra that it is centerless, or if you want to, that G is actually the commutator algebra. Right? Okay, so if G contains a non-degenerate subalgebra of even dimension, which is its own centralizer, then it admits an exact two-plectic form. And here, which is interesting, is that as a consequence, notice that in a semi-simple Lie algebra, you have your Cartan form, your Cartan algebra, which is its own centralizer. So if the Cartan algebra has even dimension, then you have that the Lie algebra itself has a two-plectic form. And since the dimension of the Cartan algebra is actually the dimension of the Lie algebra in the semi-simple case, then we have that every semi-simple Lie algebra of even rank, if you want to, of even dimension, admits an exact two-plectic form. Okay. Now, some more perfect cases. Can we generalize that to other non-semi-simple cases? And the cases, actually, yes. And for instance, if we take the perfect quadratic Lie algebra and we have a subalgebra H, which is its own centralizer, then the cotangent algebra, this means the T star extension by 0 of the Lie algebra of G, and also admits a two-plectic form. Okay. In particular, if we apply this to semi-simple Lie algebras, then the cotangent algebra of an arbitrary semi-simple Lie algebra admits an exact two-plectic structure. And I have to mention here that, in principle, I don't know if I don't know if you remember that when one had a perfect quadratic Lie algebra, the first example of two-plectic structure that we constructed was B of bracket X, Y, Z, right? And obviously that two-plectic structure is in general, it is not two-plectic. In general, it is, I think it is never exact. Now I am not sure, but I think it is never exact. But but here we see that in those cases we can also have exact structure. So we have some let's say different non-trivial two-plectic structures that are not the standard one. And this is and that is why it is difficult to see, even for the semi-simple case, if the Lie algebra G plus the one-dimensional Lie algebra cannot have a two-plectic structure, because one has to take all possible two-plectic structures and see that they cannot be extended to the direct product, which is not so simple. Okay, I'm about to finish. Just sorry. I don't know why sometimes it doesn't work. Okay, so just in order to finish, just let me pose some open problems. The first thing is that, well, obviously, we have that two-plectic algebras. We have constructed many of them by a quadratic double extension, but we know that not every two-plectic structure comes from a two-plectic Lie algebra in the middle. So maybe you have you have a quadratic Lie algebra which is two-plectic. It is obviously a quadratic double extension of something, but maybe the Lie algebra in the middle does not have a quadratic, sorry, a two-plectic form. But what it is true is, well, there's one case which is very obvious. Just think of a two-plectic quadratic Lie algebra of dimension 6. For instance, the T star extension by 0 of the Heisenberg Lie algebra. It is a double extension of a four-dimensional Lie algebra which cannot be two-plectic. So we have then some two-plectic quadratic Lie algebras which cannot be constructed as the double extension of a two-plectic one, right? So we know that that happens in the two-plectic case, but maybe in the exact two-plectic case, and remember that, for instance, that case that I mentioned of the T star extension of the Heisenberg Lie algebra did not admit any exact two-plectic structure. So I have the feeling that this might work. So that not for two-plectic Lie algebras, but for exact two-plectic Lie algebras with quadratic forms, one can always have a theorem of double extension like, in the sense that every exact two-plectic quadratic Lie algebra can be obtained as the quadratic double extension of a lower dimensional exact two-plectic quadratic Lie algebra. I think that this, I conjecture that it is true, but we have not proved it, usually. Okay, Lorentz quadratic Lie algebras are only oscillator groups, and they are always two-plectic. Well, are either oscillator groups or abelian, and they are always two-plectic. So maybe one reasonable way to follow that situation is, or to extend the situation, is to see what happens in the cases when one has a quadratic metric of index 2. And these quadratic metrics of index 2 have their importance linked exactly with the next point there, the next item there, which is if pseudo-Hermitian quadratic Lie algebras admit two-plectic or exact two-plectic structures. What is a pseudo-Hermitian quadratic Lie algebra? Just to to give the definition very quickly. You have a quadratic Lie algebra, but besides you have a complex structure on the Lie algebra such that it is skew-symmetric with respect to the quadratic form. And in those cases, one easily sees that the metric cannot have index 1, and the smallest index that appears is index 2. I've been quite interesting in this case of pseudo-Hermitian quadratic Lie algebras because this is the subject of thesis of one of my students. So I think that it is a problem that could be of interest. We do not know if every pseudo-Hermitian quadratic Lie algebra admit two-plectic or stacked two-plectic structures. But I am also quite optimistic here because I think that the importance of even dimensionality in this problem is quite important. It's quite relevant. So I think that maybe there we could get some results also. And okay, yes, another thing that I had also mentioned before is that Medina and Rebois and Dardier defined a method which was similar to the method of quadratic double extension, but for symplectic Lie algebras, and it was the method of symplectic double extension. Maybe we could see that symplectic double extension can be used to give some description of the symplectic and twoplectic cases. For instance, if you remember, we had that symplectic quadratic Lie algebras were always twoplectic. So there we have some examples of symplectic Lie algebras which are also twoplectic. So can we redo these results that we have had in the quadratic case for the symplectic case? And that was the reason, if you remember, when I mentioned our main theorem, that is the reason why there we used just a double extension-like method, but we did not impose the conditions first of being quadratic, just being a sort of double extension in the sense that our big Lie algebra was the Lie algebra obtained by a central derivation and then a semi-direct product. And so maybe in the case of symplectic Lie algebras, we can also say something, and that would be also interesting. I mean, that is a very interesting problem also to see if, even for the quadratic case, I mean, to see if it always happens as here. I mean, if you have one Lie algebra, which is, let's say, quadratic and k plectic, if it is always k plus 1 plectic. Which I don't know, but it would be a very interesting case out of the twoplectic cases, actually. Okay, and with this, sorry, I finished. Just want to thank you very much, and if you want the reference of our papers, that one. Thank you.
Thank you very much for your interesting talk. Are there any questions? Or comments or remarks? Ivan, do you have any question?
If you ask me, then no. I just
Okay.
to show that I exist.
Okay, if there are no questions, let's thank the speaker again.
Thank you.
And we will resume on next Monday at the usual time.
Okay. See you.
See you. Bye.
Oh.